everyone. I'm Paige Martin, and I will talk today about some of my research on idealized ocean atmosphere modeling that I have worked on with Brian Arbick at the University of Michigan as part of my PhD, which I finished last year, but I'm still finishing up some of this work now. So let's start with the big picture. We have the ocean, we all know what that is. We have the atmosphere right on top of it. And what I'll be looking at, what I'm very interested in, is ocean-atmosphere variability. So how the two fluids, how the ocean and the atmosphere, vary in time and space. And I'm specifically interested in this talk about what happens at the surface. And so there are a lot of exchanges that happen between the fluids at the surface, including momentum exchange. For instance, you have the atmospheric winds that blow on the surface of the ocean. You also have heat exchange between the two fluids. There are also internal dynamics, and the internal dynamics can affect what happens at the surface, which therefore can affect what happens in the other fluid and might actually affect the what I'm calling internal dynamics in the other fluid. And as you can tell, it gets pretty complicated pretty quickly. So I'm trying to help tease apart a little bit about what's going on here. We often look at ocean-atmosphere interaction by looking at the surface temperature field. So that turns out to be play a significant role here. And the method that I will talk about here is that I will look at surface temperature variance. And by variance, I basically mean variability. And I'll be looking at budgets, which means kind of what makes up the surface temperature variance field. And I'll be looking in both fluids in the frequency domain. And the frequency domain allows me to look at the different timescales of variability, because these processes depend heavily on different timescales, whether it's minutes or decades, or kind of anywhere on that spectrum. So my main question is, what are the processes that generate surface temperature variability and at what timescales? So I study all this by running the Quasi-Geostrophic coupled model, or Q-GCM. It is a very idealized model. If this is our real globe, the model tries to mimic the real North Atlantic Ocean by creating a square-shaped ocean. So not quite the North Atlantic as we know it, but roughly. And the atmosphere is just the rectangle right on top of it. So no actual continents. That's all we've got. So here's the ocean in the model. I'll lay that down. There's the atmosphere. This is the sea surface temperature and the atmospheric surface temperature where they meet. Then the atmosphere has 3 layers in the vertical and 3 layers in the ocean as well. And so this is what makes up the full model. Here I will play a little video so we can just see a little bit of the dynamics that happen in the model. So you can see this is the surface temperature in the atmosphere, and you can see these waves propagating along the channel. And you can really see the land-sea contrast. That's what you see here in this box. That is the ocean, and you can see how the waves are really damped here. They behave quite differently in the ocean compared to the atmosphere. So you can see the communication between the two fluids right here. And guess what computer language I use to do my data analysis? Yep, you probably guessed it. Python. It's the best. If you don't use it already, you should. So really quickly, I'm going to just show one example of a plot that I've made with some results. But beforehand, I want to make sure we understand what we're seeing. So on the x-axis, we'll see frequency, which is basically 1 over time. So we have low frequencies and long time scales on the left, and high frequencies and short time scales on the right. If we have a curve that looks like this, we interpret this as when it's positive, it's adding or driving variance in the system, whereas if it's negative, it's removing variance or damping the variance in the system. So let's take a look at this. So we have these envelopes here just for some added statistics. That's the 90% confidence interval. But what we can see here, we have frequency on the x-axis. We've got kind of a 30-day time scale over on the right and 10 years over on the left. And we can see that these terms defined over here actually do behave quite differently at different time scales. And so this has really helped us to kind of understand what, or give us a very, very little peek at what might be actually generating this surface temperature variability. Very briefly before I end, I wanted to say that I will be starting a new position as a postdoc at Columbia University next month with Ryan Abernathy. And he and several others have really gotten this community platform called Pangeo going. It's great if you like Python or computational science. Check it out. What I will be doing there is I'll be doing some mostly climate science, a little bit of data science, and really working at where they intersect. So really building tools while doing climate science. So I want to thank you for listening, and I always sneak in a photo of a handstand if I can. This one's very appropriate. It's me handstanding at the ocean-atmosphere interface. Thank you very much.